Going to look at a new digital multimeter that I got today. We're going to take this one apart, take a look at it. I'm going to put it through its paces and put it up against my Fluke, and we'll see how it stands up. Should be an interesting one. Let's check it out. Today we're going to do a quick review of this new meter I just received. It's by Kaiweets. It's a model KM601. They say it's a smart digital multimeter. Brand new. This one has not been opened yet. This is the official unboxing. It just arrived in the mail today. So let's break the seal, and take a look at what we get in the package. Of course, it comes in a case. Comes with 6 AAA batteries and a user's manual. First things first, let's take a look at the meter. Let's check this bad boy out. Wow, okay. Comes with a temperature probe, and of course some 600 volt rated test probes with the protective caps on them, which can be removed. I think this should be able to be removed. There we go. So we have our conventional probes, and we have the protective caps to prevent you from shorting things out, which most good meters will have. 10 amps rated, 600 volts. Here's the meter itself. Has a flashlight, it looks like, on it. And first, I guess we got to put the batteries in it, so got to figure out where the batteries go. Pop it out of the case. Comes in a rubber case like a cell phone. Even comes with a warning to remove the leads before taking off the back. That's standard, and that would be a given, that you would always remove the leads before removing the back. I don't know if I got to take all those screws out or just one. Well, I guess just one screw has to come out. Well, we'll take the other ones out anyway. At some point, we're gonna open this up. But it takes 3 batteries. They give you 6 in the package, so you get a spare set of batteries. So we'll just open these ones up and take a look at the high quality Kendall batteries. They're alkaline batteries. I wonder how long these will last. Well, I guess we'll find out, as I'll probably end up using this meter a bit on my bench, especially if it turns out to be a winner. And the batteries go in. And then, of course, ooh, it's got a color LCD screen. Isn't that kind of cool? Slip it back into its case. Looks like we've got some non-contact voltage detection. And there's a light on here. You can click the light on to illuminate dark areas. It's not a very bright light, but hey, it's better than no light, I guess. We'll plug the probes in. It's telling me the temperature here in the shop. It's 13.1 degrees Celsius. It actually has a thermometer built in to tell you what your temperature is. And our probes, we have 4 different inputs on the bottom here. It has a common input for the common plug, and normally your red would go into the standard measurement connector. For measuring currents, we have a milliamp and a 10 amp rated with a fuse. 10 amp rated fuse for one, 600 milliamp for the other. And we'll open this thing up to find where those fuses are shortly here. Let's see here. How does this thing work? Well, it's auto function, and then you can select DC voltage, select ohms, and it tells you which, it flashes and tells you which to plug your leads into. Okay, ohms, volts, and this one here is nanofarads. It looks like that's capacitance. It tells you right up here too. If you look on the top, might be hard to see with all the lights in here, but at the top it tells you what you're doing. So this is millivolt. Looks like a millivolt AC or no DC. Frequency in hertz. Celsius or Fahrenheit, so we can convert. It's 56 Fahrenheit, 13 Celsius. That's the temperature that's in here now. And then non-contact, this is for testing for non-contact voltage. AC milliamps, looks like, and you move the leads over. It tells you lead, and it's telling you where to move the lead to. So if I plug the lead in there, it's going to beep and tell me that it's ready to go. And if I go to the next one, it'll be, where's auto function? Where is we here? Where do we select? And then amps, it's telling me to move the lead over to this one. And it knows when I've plugged the lead in. And then if I remove and then go back and press the auto button, now we're back to, it's going to select between voltage and ohms. You see? It's actually detecting voltage, ohms, or continuity automatically. So if I short the leads together, it's going to tell me that there's 0 ohms. And it sets off the buzzer. So now it's looking to see what I'm going to measure. We're going to measure a few things here. I'm going to turn on my power supply and we'll set the voltage to 3.7 volts. And I will measure that. We'll also measure a few other things, but let's just measure DC 3.7 volts. I'll connect my meter up here. I'm going to get rid of these sissy probes, as I like to call them. I like real probes, ones you can cause short circuits with. Connect up the meter here and measure DC voltage and see that it measures 3.755 volts, which is probably right on the money. Let's just check it with my fluke, because you know, if it's accurate, it will be a fluke, and see what the fluke meter tells me that we are actually outputting from the power supply. Whoops. And it should read relatively close to what this other one's reading. So 3.75 volts. I think we're in the ballpark. So my fluke's measuring 3.744 and this is measuring 3.747. I think we're probably in the ballpark. If I crank the meter, or if I crank the power supply up to 12 volts, what happens? .0 volts on my power supply. Okay, 12.0 volts. Pretty darn close. 11.99. What's the fluke say? 12.02. So we're close. We're close. Good enough. So for DC voltage, it passes. If I want to measure, say, a battery, we grab a non-rechargeable lithium battery here. We'll see what the voltage on this non-rechargeable lithium battery is. We'll take a look at it first of all on the fluke, which tells me it's 3.51 volts because this battery is not new. 3.51 volts. And on this meter, 3.518 volts. Looks pretty darn accurate measuring DC voltage. Let's check it out for AC voltage now. Now, according to the smart feature here, I should be able to just plug this in to AC. I've got my AC power cord here. I should be able to stick this in and it should switch automatically to AC and give me a voltage reading if my plug would connect. 119.5 volts. Probably what it is, because this is obviously going through my Variac. 119.5 volts AC, true RMS. Let's see what the fluke says. Now the fluke is a little different. I have to actually switch the fluke to AC or it won't measure because it's not smart. It's a dumb meter, but hey, it's old. 119.8. Kind of looks about the same. 119.8. And this one was 119.8 as well, I think. Once it figures out that it's AC, okay, 119.5, close enough. And it tells me that the hertz is 60.0 hertz automatically. I don't have to guess. I don't have to switch it to anything. It's automatically going to tell me what the frequency is. So far, so good. Let's measure some resistors. I have here a resistor, 4.7 meg, yellow, violet, blue. Let's just take a look on the fluke and see what the fluke tells me that this is. Now, because this is a high resistance resistor, I'm obviously not going to want to touch the probe with my fingers because my skin resistance will change it, because this is a high value resistor. I first have to change the fluke over to tell it that I want to read ohms, and we'll put the probes on here, and this resistor actually does measure 4.88 mega ohms on the fluke. Okay, smart meter. What's smart meter going to tell me? Again, I'm not touching anything. This is going to figure this out automatically. And we connect the resistor, and it measures it, and it says it's 4.882 mega ohms. A little M down here. Might not be easy for you guys to see with the reflection. Let me just put that battery down below there so you guys can see that it is 4.886 mega ohms. And it's 14.7 degrees Celsius in here. So that one measures good. Let's try a lower value resistor. What is this one here? Well, let's measure it and see. I'm not even going to look at the color code. We're just going to measure this. This is 67.7 ohms. 67.8 ohms. How does the fluke tell me? 68.2. Pretty darn close. I think that's a pass. Let's measure our probe resistance first of all on the fluke. My resistance is 0.7 ohms on the test leads. This one here will probably measure 0. 0.5. No, 0. So it's zeroing itself out. So we know that it measures resistors, and it measures AC and DC voltage accurately. Next, let's measure some electrolytic capacitors and see whether it measures the capacity of electrolytic capacitors, how close it is. Now, for capacitors, I have to, I believe, go into another mode here, because this is just for voltage, ohms, and a continuity test. To do capacitors, I actually have to switch it. So I have to switch it to capacitor test, and I have to switch my fluke to capacitor test. So now I should be able to measure capacitors, and it should tell me what the capacity is. So here it is on my fluke. Let's check out the fluke. Got to get my polarity correct here. This is what is this one? A 330 microfarad capacitor. It's brand new. So let's see what the fluke shows me that this capacitor is rated. I don't know if you guys can see that with the reflection, but 322, 321 microfarads. We'll short the leads, discharge the capacitor, and we'll measure it up with this one. And tell me what this one gets to. It's charging up. 317.3 microfarads. Pretty close. Either one of them is going to be an accurate reading, or fairly accurate. So it measures capacitors. Let's try a bigger one. Let's try a 1000 microfarad capacitor. So we'll discharge it first, make sure that there's no charge on the cap, and we'll just connect the probe and watch it measure. It's in nanofarads now, so it's got to figure out that it's actually microfarads. It's charging up the cap, and it's measuring the capacity, and it's 1073 microfarads. It's got a point there too, but it's because it's gone to MF instead of UF, right? So it's 1073 microfarads. If I go to my fluke, if it's accurate, it'll be a fluke, remember? That's the gold standard, isn't it? 1090. Okay, a little bit higher. Which one's accurate now? Is it the fluke or is it this one? My fluke's very old, so. But again, with capacitors, as long as you're within that sweet spot, that range, you're generally considered okay. Pick a smaller one here. This smaller cap is a, what is this one? It's a 47. So 47 microfarad. 49.3 on the fluke. And $48.7. You see, it's showing microfarad here. When I was measuring the 1000, it went to M. So then the decimal point moved over by 3 points. And I'm assuming this thing probably could even measure some of those super caps too. It would certainly take a long time to charge them up. Incidentally, it comes with a 3-year warranty. Should have probably opened the manual first. What do you think? But nobody likes to read manuals, especially me. I don't like reading manuals. I find reading manuals is kind of boring. But anyway, it just gives you the warnings and the symbols and so forth. I just want to see what the specs are and what it will do. So, and what other features we've got here. So, power button is where's the power button? There's got to be a part on here somewhere. Was it on the side? Auto power off. Yeah, the power button's on the side here. So auto power off turns on and off the power automatically within 15 minutes. Without any operation, in about 15 minutes, the meter will turn off 1 minute before it turns off. There'll be 5 beeps. So there's a power button on here somewhere too. There it is on the top. Power button on the top to turn it off. And of course, the auto power off will turn itself off after 15 minutes of non-use, and that's this button on the side here. You can select it for auto power. It says, do not measure voltages higher than 1000 volt DC or 750 volts AC, or the meter may be damaged. Okay, I don't think we need to worry too much about that, but that means don't go measuring horizontal output transistors, for example, because they have a pulse of well over AC 750 volts, or typically closer to a kilovolt. But then, hey, my fluke, it has a maximum input of 600 volts, so it's stacking up quite nicely to the fluke. What I want to test with this, and what I will test with this, is we're going to take apart a CRT television, and I'm going to measure the video outputs on the back for DC voltage, because that is something that a lot of meters have trouble with. And a lot of meters won't measure it because the influence of the AC video signal is going to cause problems. My fluke will measure it accurately. My old Radio Shack meter, for example, that I got like 30 years ago, will not. So resistance measurement, continuity, capacitance. I just want to see what the diode test, of course. It'll do diodes. You just push the button for the diode test, and it will give us a reading of the voltage drop. Diode test feature. I've got a standard bipolar junction transistor. So NPN, my positive on the base, 0.6 volt drop, emitter to base and collector to base, 0.6 volt drop, and of course it'll measure open the other direction because the junction is only one direction, and if the diode was shorted, it just shows 0 on a shorted diode. Millivolt measurements, and that has to be done manually. You select with the selection button. That's millivolts AC and DC. Hertz, well, it does that automatically, but it also, I guess, give you the duty here. So if I were to measure my AC incoming line when it's in frequency mode, it will show me it's 59.99 hertz with a 49.9% duty cycle. So pretty darn close. Should be 50-50. It should be 50%, but it shows you your duty. There we go. 50%. There we go. 60 hertz exactly. 50% duty cycle. That's what we would expect for sine wave. But again, if you're measuring something that wasn't a sine wave, then you would get the duty cycle for one side of the phase versus the other. So that's interesting that it does that. It will measure the frequency in hertz and the duty cycle temperature measurement. You put one pole into the live side and the other one into common, and it'll measure in Fahrenheit or Celsius. It says put your thermocouple on and touch the end of the thermocouple to the object being measured, such as a soldering iron, for example, and it will give you the temperature in either Fahrenheit or Celsius. Non-contact AC voltage, well, that's exactly what that is. You just hold the meter near a live wire, and it should let you know that you're holding it near a live wire. I just so happen that I have such a live wire right here, and when I bring it near here, it should tell me that there's voltage present. Which it does. It beeps to tell me that, and the light turns red to tell me that, hey, there's voltage here. Okay, so to check out the contact, we had the non-contact first. To test out the contact, and they say don't have the black lead plugged in. That way nothing can short out. You just have the one red lead plugged in. And if you go up to your outlet or your circuit under test, of course the light. Of course the live side is the smaller of the two on North American plugs. The neutral side and ground is the large side and the ground prong. And as you can see, nothing, right? Nothing. I get the other side here, and it's flashing red, and it's telling me this is the live side. Okay, it's going to show me the temperature in Fahrenheit and Celsius. Let's just see what the temperature of the soldering iron is now. And it's just been running for a few minutes, so it's probably still getting up to temperature, but let's just see what it says the temperature is. We'll see what it finally settles into, and then I'll pan the camera over to what my dial is set to, so you can see how accurate it is. Now, say I calibrated this iron about, I don't know, 4 or 5 years ago. It's set for 710 degrees. 4.62, 4.64. We're pretty close. Pretty close in current measurement. Last test I'm going to do is I'm going to measure a complex waveform. But what I want to measure is I want to measure the output, the video outputs on the television, because good meters will let me measure the DC voltage, and bad meters may give a bad result, a false result. So good meters will let me measure the voltage, 117.4 volts on the red, 121 on the green, and the blue over here. So 127 volts. That's what I expect for the DC component. Let's see how this one fares. Okay, voltage wise. Hey, 120 volts. Looking good. The green, 132 volts, and the blue, 123. And of course the G2 voltage, 383 volts. And we can measure the G2 obviously on the fluke as well. 383 volts for the G2, and the G2 here is 384 volts. So it's a pass. Okay, I think that just about does it for the measurements on this. We're going to take this thing apart momentarily. I'm just going to put this little TV back together and get it out of here. We're going to take this one apart. I just want to take a look at the build of the inside, and then we'll finish up this one. But so far, I'm pretty impressed. Okay, now we'll take this one apart, pop the case off, and take the back off of it. We have to remove the battery cover first. And this is also where the fuses live if you ever have to change the fuse. There's an indicator that comes up on the screen that tells you that the fuse is blown. Remove the 4 screws that hold the back on it. So here's the back. I'll get you guys a close-up. Got your 2 fuses here. Didn't have to take the batteries out. The battery terminals just contact to the back here of the unit. But here is the 2 fuses for the 10 amp and the 600 milliamp. The 10 amp fuse is probably this one over here, F2, I would think, is the 10 amp fuse. And then the other fuse is over here. It's using ceramic fuses. Let's just take a look at the fuses themselves. 10 amp, 250 volts. Looks like UL certified. And this one here is 600 milliamps, 250 volts. Here's the main board itself. Everything's buried down inside one IC. 2 ICs. Looks like. There's a buzzer on the back here. And your non-contact monitor up here. Which should just be a little probe. It should just be a little metal probe that sits in behind here. Just to measure any induction. There's the LED for the little flashlight. Kind of useless, but I guess if you're in the dark and you've got no other light, it gives you some light to work with. And that's pretty much it. Yeah, a little simple little unit. Build quality looks to be okay. I don't see anything jumping out at me that says this is no good. There's a fair bit of isolation in here, and there's generous spaces between the high current conductors. Our voltage comes over here. There's a PTC across here for clamping transients, and I would imagine if you exceeded the maximum voltage, this PTC would clamp everything down, short it out, and pop the fuse. It's more than likely what's going to happen if you over voltage it. This is going to pop this fuse, because this is the main fuse that everything, regardless of whether you're measuring current or voltage, everything's going to go through that fuse. So that's your main protection. So if you were to over voltage or overload it, this PTC is going to make sure that that fuse blows. Build-wise, this looks very good for a basic meter. So I'm going to throw this one back together. This one's going to be become part of a long-term test. I'll be using it on my bench. Going forward, it'll sit here and complement my existing equipment. There. Anyway, that's basically it. I'm going to put a link in the description to the Kaiweets True RMS KM601 multimeter. Thanks for watching.